produced by a current is the mu naught constant times the current divided by 2 pi r, where r is the distance away from the current. This magnetic field forms a circle going around the current. And the direction of that magnetic field you get from the second right-hand rule, which would say your thumb in the direction of the current, and then your fingers go around the thumb, so they curl around the thumb in the direction of the magnetic field. So again, like if you got current going into the board, away from you, magnetic field would be going around clockwise. And it's tangent to that circle at whatever point you're looking at. Where the R then would be from the current to this location that you're finding this. Again, this equation, we're assuming the wire is infinitely long and straight. And we won't do any problems where it's not infinitely long and straight. Okay. If the current is coming toward you, then it's going around the other way. Going around counterclockwise. So thumb coming out, fingers go around counterclockwise, thumb going in, fingers go around that way. If it's going like to the right, that way, and then as your fingers are above the current, they would be coming out of the board and below the current, so current this way, fingers going this way around, magnetic field would be going into the board. Of course, it's coming around something like that, which is just hard to draw. It's easy to draw if it's coming either straight out of the paper or into the paper. But if it's going in the plane of the paper, you can still do it. It's just on one side it's going in, one side it's going out, depending on which way the current's going. So that's the magnetic field formed by a current some distance away from the current. For a coil or a solenoid, same, just a different word for that. Magnetic field down the center of the coil is the mu naught times the number of turns in the coil, number of loops times the current divided by the length of the coil. So you had like this would be one of those where you have to have the picture drawn so you can tell which way the coil is. So if you've got current going in this way, coming out this side, then the direction of that field down the center line, that would be the magnitude. Direction is that third right-hand rule. And you say your fingers curl around the coil, direction the current's going. I'm going from the front side around to the back side, and then the thumb of your right hand tells you which end is the north pole of this magnetic field. So we had that. If you've got the charge moving in the magnetic field, the F is QVB, assuming V and V are perpendicular, then that force, which would be the QVB, is a centripetal force, causes it to change direction and not speed it up or slow it down. So that's equal to the mass times that centripetal acceleration, V squared over R. Solve that for R, and you get R is equal to mv over qv. So all of this gives us that equation. Used it back then, again with relativity. Should be in the next to last problem set. There's a question about like, if you accelerate the proton and the electron across some big potential difference. They both become relativistic speeds. So you got to use that relativistic kinetic energy to find the speed of it. But then what's the ratio of the radius of the whatever proton to the radius of the electron, whichever way that is. Well, you've got this as your radius when you go into this magnetic field, and so it's proportional to the mass of the proton, the speed of the proton over Q and B, divided by the mass of the electron, speed of the electron over Q and B. Of course, if it's relativistic, then not only is the speed relativistic, but also the mass is relativistic. So you have that mass is the rest mass divided by that square root of 1 minus v squared over c squared term. But it hasn't, not only that Q delta V is equal to the not 1/2 mv squared, but that relativistic kinetic energy. Then you're going into a magnetic field, and so you've got the R as the mv over qb equation to deal with. And the m is changing in both of them. So anyway, that was that, dealing with a charged particle going perpendicular, so you have sine of 90 here, which is at 1, to a moving through a magnetic field perpendicular to the field, causes it to go into a radius as it circles, and you can use that to find the radius. But again, it's coming from the force is equal to the mv squared over r. At that, chapter 29 got into Faraday's law of induction. So magnetic flux was the V times the A times the cosine of the angle. And yeah, it's technically an integral of V dot dA if you got a changing V sort of a thing, but we won't do anything. We're going to have to do the integral of V dot dA. So it's just the V times the A times the cosine of the angle between them. Remember, the area vector is perpendicular to that area surface always. So like your coil, the area would be like cross-sectional area, and the area vector then would be the going out or going in, depending on which way you're looking at it at that point. But that's the magnetic flux. Then if you've got a changing magnetic flux, you're going to induce a voltage. That strip E is a voltage, just like the V. And the technical equation for that is minus number of turns in a coil, if you've got more than one turn, and whatever N is. Change in the magnetic flux with respect to time, or if flux is a function of time, or B is a function of time, or A is a function of time, or theta is a function of time, any one of those, then you got minus N times a derivative of the flux with respect to time. So if any of those are time-dependent equations, then you can do a derivative to find the induced voltage at some time. There was that question on that test about like what was the maximum current when and you're given the flux as a function of time. Okay, so you took the derivative to find the voltage, and voltage was current times resistance. You knew the resistance, so current was this voltage divided by the resistance. Then you had to find what was the maximum current. Actually, one easy way to do that was just to take the derivative of the current with respect to time, set it equal to 0, and then that was where your either minimum or maximum was at that point, back in calculus. So induced voltage. If you've got just a link, not a loop of any sort, or multiple loops, but just a length of conducting wire moving through, or conducting material moving through a magnetic field, induced voltage would be the magnetic field times the length of whatever's moving times the speed. like the airplane flying through the Earth's magnetic field. They are that antenna on the truck as it moves through the Earth's magnetic field. There's an induced voltage on it. And depending on which way it's moving and which way the Earth's magnetic field is, then you get either like top positive and bottom negative, or vice versa, or maybe just the front side of the antenna positive and the back side negative. So it depends on how you're looking, or which way you're looking at that. So we got that for just a certain length, moving at a certain speed through a magnetic field. If you've got changing current in a coil, or just changing current anyway, induced voltage would be minus the inductance, which is for a coil, and times the change in the current with respect to time. So d/dt. So if you've got a coil current going through it, but it's not constant current, the current is changing, the magnetic field is changing, but if the magnetic field is changing, flux is changing, and so you get this induced voltage at that point. So those are all the various induced voltage formulas that we had. If you've got an RL circuit, so you've got a resistor and a coil and the inductor in series hooked up to a battery. And it says in AC, this is a battery. You close the switch to connect the two together to the battery, and you get current as a function of time, is the V over the R, and then times your 1 minus e to the negative R times the time divided by the inductance. Voltage on the resistor would be the battery voltage times the 1 minus e negative RT over L. And the voltage on the inductor, the coil, would be the V times just e to the negative RT over L. That's an induced voltage coming from this. So the d/dt brings it down to just e to the power. So it's a decreasing voltage with time as it progresses. Or the voltage on the resistor increases with time up to a maximum. So we had those equations. Again, that's just batteries if you've got a voltage there, or a induced voltage because of one of those things happening. Last thing we did there was with AC circuits. You had like a resistor, capacitor, coil, or an inductor in series, and you're going to hook it up to a AC that has a certain frequency with it, voltage and frequency. Then the Chi sub L, which is that inductive reactance, that's the effective resistance of the coil in the AC circuit, was the 2 pi F times the inductance. The Chi sub C, capacitive reactance, 1 over 2 pi F times the C. The total resistive effect, or the impedance, was that square root of the R squared plus the Chi sub L minus the Chi sub C squared. And then the phase angle between the voltage and the current going through here would be the Chi sub L minus the Chi sub C over the R. You can get that. These come from that phasor diagram. So you had like your R, Chi sub L, Chi sub C, and so the difference between the Chi L and the Chi C, and then the Z is the hypotenuse of that, and the phase angle is given for that one. Remember the voltage on the resistor is in phase with the current, so that voltage on the resistor is either say the positive X direction. And then the total voltage is some phase angle to the current. Think of the current in the X direction, voltage on the inductor in the positive Y direction, 90 degrees ahead of the current, voltage on the capacitor, negative Y, so it's 90 degrees behind the current, and you get this relationship. So we have those things. Again, the total voltage is the current times that total impedance. So V is I times Z. Power in your AC circuit, I times V times the cosine of the phase angle. And the cosine of the phase angle then is called the power factor. And that. Resonant frequency for an AC circuit, where you get the maximum current and maximum power, was when chi L is equal to chi C. So these two are equal, phase angle is 0, and you get, then when you put these two equal to each other, you get the F is 1 over 2 pi square root L times C. Is that equation? This RL circuit. You got a coil in your AC or in the DC circuit. You got current going through the coil that produces a magnetic field. Energy stored is the 1/2 inductance times current squared. The 1/2 Li squared if it's energy stored in the magnetic field of a coil. You've got current going through the coil. So we had power, resonance frequency, transformers. If you've got a transformer, you've got an input current and voltage, you've got an output current and voltage, you've got a certain efficiency. And so the ratio of the voltages is equal to the same as the ratio of the number of turns on your two sides, and then the efficiency times the I1 V1, that's the input power, is going to equal the I2 V2, or the output power, primary and secondary IV. So if it's a transformer problem, we got those equations we can use to try to work it. And then the last thing on electromagnetic waves in general, again, speed is frequency times wavelength, but for electromagnetic waves, speed is the speed of light at best. Then we got the optics. So for optics, index of refraction, speed of light in a vacuum divided by the speed of light in the medium, whatever this is. And N is always greater than or equal to 1. Equal to 1 for a vacuum, greater than 1 for anything else. So this speed is less than the speed of the vacuum. That's Snell's law, so your N1 sine theta 1 equals N2 sine of theta 2. That product has to stay equal. The thetas, remember, always measured to the normal to the surface, not to the surface itself, but to the normal, perpendicular to the surface. For total internal reflection, that sine of the critical angle is the N2 over N1, where N2 must be less than N1. If you're in the bigger index, light's going from it. If it's less than this angle, it refracts according to Snell's law and goes out into the smaller index, but it's bending away from the normal. But if it's equal to this angle, then the angle of refraction is just 90 degrees right along the surface. If the angle, the theta 1 is bigger than this critical angle, then there's no refraction. Everything reflects and stays inside the first median. That's that total internal reflection. Had that. Mirrors and lenses. And we've got two basic equations, one over the object distance plus one over the image distance is equal to one over the focal length. And the magnification is minus the Q over the P, or the height of the image over the size of the object. For mirrors, on the front side it's positive, on the back side it's negative, and that's for P or Q. Focal length is positive if it's concave, which means it's on the focal length is on the front side. It's negative if it's a convex mirror, curved toward you. By the way, for the other one here is that the focal length is 1/2 the radius of curvature. If that helps with anything. For a lens, P is positive on the front, negative on the back. Q is positive on the back, negative on the front side. The difference between mirrors and lenses. And focal length is positive if it's a converging lens. Think of the magnifying glass type lens. And it's negative if it's a diverging. Again, like on this last test, we had a problem that said it was a convex mirror. So you had to put the focal length in as a negative number, even though it didn't tell you it was negative when it gave you the number. That the focal length of this convex mirror is 20 centimeters. That's the magnitude. But it was convex, so I had to put it in as a negative 20 for the F in that equation. Or if it says a diverging lens, focal length must be negative. And so we had that, and then if it was a double lens type system where the image of the first lens becomes the object of the second lens, then the total magnification is the product of the individual lens magnifications. We had those equations to deal with. So that was mirrors and lenses, which is part of chapter 32 and 33. And then, that the lens maker's equations. No, I'm not going to ask you anything about the lens maker's equation. Interference or diffraction. So your Grady, you have the D sine theta is equal to M lambda. M is 0, 1, 2, dot, dot, dot. The tangent of the angle is the y over the L. Think of your Grady L distance to the screen. The y is how far away from the 0 point are you? And here's your theta. And the d is the distance between it. The d is 1 over n, where n is the number of openings or lines or whatever they're calling it per unit length. So again, those gradings we used in the lab had 600 lines per millimeter. And so you'd have 1 over 600 would be the distance between them in millimeters. But in the equation, the d sine theta equation, I would always say put the d in meters. So your lambda is also in meters. D and lambda need to be in those same units. So we've got those equations dealing with diffraction. Again, if it's only 2 openings, then they're probably going to tell you the D number. Or maybe you're just solving it if there's only 2 openings. If it's multiple openings, then I use this to find the D. That's the D times the sine of this angle is the M. So this is for constructive interference. M is 0 or 1 or 2, however far you got for that. So it's equal to the M times the lambda. For polarization, only equation we had was by reflection, and we had that tangent of the polarizing angle is the M2 over the M1. So M1, M2, here's your polarizing angle to the normal. You got reflection, that's the 100% polarized, and refracted ray down here, and when you're at this angle, these two mediums, these two are perpendicular to each other. And you got 100% polarization on reflection. And then the other thing that we had is resolution. And so the minimum angle of resolution was the 1.22 wavelength over the diameter of a circular opening that you're looking through. And that could be the pupil of the eye, it could be the diameter of a telescope, it could be the diameter of a radar dish, not holding a fence, whatever. It's the diameter the light is going through, and this is your minimum angle, so you can tell either that you've got two separate things, you can actually see them as separate things, or it could be like two sides of the same object. But assuming that's the minimum angle to separate these two things, and then the distance between them, S, is equal to the distance they are away from your opening times this theta. So you got your D, and your R, and then here's the S. Here's your theta at that point. So here's your two light sources, which could be either two separate light sources, or it could be two sides, lights coming from two sides of the same object. So for resolution, we can work with those two equations. And that was all, everything on optics. For chapter 36 on relativity, that time dilation, delta T is delta T naught over the square root. Length contraction, L equals the root. And then the mass, effectively, is the rest mass when it's not moving, divided by that square root. C squared over C squared. M naught here is always the mass of the particle or whatever the object is when it's not moving. This is the effective mass when it is moving, or what appears to be the mass when it is moving. The delta T naught, that would always be the spaceship. Delta T would be the Earth. Or the delta T naught would be the time for, say, like that muon. It will last so many microseconds before it decays into whatever it's going to decay into. And then the delta T would be the laboratory time, or what the Earth says the time is. The L and the L naught depend on whose viewpoint you're looking at it from. But remember, the time, this time always has to be less than, or excuse me, more than this time, because the square root's a number less than 1. So Earth time is always bigger than spaceship time, or the lab time is bigger than the particle time. The length contraction, this length is less than that length. And so if you're the stationary system and you're looking at a moving system, so you're on the Earth looking at the moving spaceship, the meter stick on the spaceship, from your point of view, looks like it's shorter than the meter stick does when the person on the spaceship says it is. Or when the spaceship isn't moving, it's 100 meters long. But when it's moving close to the speed of light, to you, it looks like it's less than 100 meters long. You would measure it to be less than 100 meters long. But if you're on the spaceship, from your point of view, your meter stick is a meter stick. But looking at the meter stick on the Earth, from the spaceship, the astronaut says the meter stick on the Earth is shorter. And his meter stick is the correct meterable size. So that can't really say that L is always this and the L naught is always that. It just depends on whose reference frame you're looking at it from. But the stationary reference frame always says that the moving reference frame's lengths are shorter than what the moving reference frames say they are. So it has that. Energy is mass times speed squared equals mc squared. Einstein's equation. And then that kinetic energy, relativistic kinetic energy, the m naught c squared over the square root of 1 minus b squared over c squared. So this is the energy of the mass. So this would be the energy, total energy of that mass when it's moving. And then if you subtract out the energy when it's not moving, m naught c squared, then this is the energy of the motion, which is then the kinetic energy. So again, if you're dealing with something that's moving close to the speed of light, you're looking at energies, kinetic energies, use this for kinetic energy, don't use the 1/2 mv squared. If it's moving at speeds less than 1% the speed of light. So 3 times 10 to the 6 meters per second. Let's cut it off at that point. Then you don't have to worry about this. You can just say kinetic energy is 1/2 mv squared. But if it's moving faster than that, better use this for kinetic energy. So we had those equations for relativistic type problems. And then radioactivity, your number that you have left, or the amount you got left, or the decay rate after a certain amount of time is equal to what you start with times the e to the negative decay constant times the time. And then the half-life is the 0.693 divided by that decay constant. So any problem dealing with radioactive substances, we'll use those equations. A lot of equations there. Make sure you got a formula sheet. I would very strongly suggest you bring in the formula sheet that I've got. You can add anything you want to that. And personally, I think there's plenty of room, plenty of white space to add what you want to on that. I know that has all the basic formulas on it. And so you're not going to be leaving something out at that point. But